Okay, welcome everyone to the continuation of this functional materials and devices session. We have 3 contributed talks before lunch, and the first talk is given by Hrishit Banerjee from the Department of Chemistry at the University of Cambridge, and he's going to tell us about external stimuli-driven spin transitions and piezochromism in metal organic complexes. So over to you, Hrishit.
Thank you. Good afternoon, everyone. I think since already the talk was introduced, I will go straight to what spin transitions and spin crossovers are and why we need to study the external stimuli-driven spin transitions in metal organic complexes, and we'll see how it goes. So what is spin crossover? That's the first question that we must ask ourselves. And spin crossover is basically a spin state switching between a low spin state to a high spin state in certain metal organic complexes, which are basically molecular species, which contain octahedrally or tetrahedrally coordinated transition metal which are joined by organic ligands. Now, this crossover can be driven by temperature, pressure, or light irradiation, or other effects like chemical pressure or substrate effect, or various kinds of effects which change the interplay between crystal field splitting and Hund coupling. I'll come to that in a second. But let's see in which materials this happens. So the transition metal coordination centers for which SCO was seen are basically the first row of the D block elements, so chromium, manganese, iron, cobalt, and nickel. And they mostly occur in 2 and 3 oxidation states, and the vast majority of these systems that show spin crossover are basically iron 2 systems. So we will mostly consider iron 2 systems and then maybe look at some other materials as well. But what we want is not a spin crossover, because a spin crossover is a very simple 2-state switching. What we really want is go to a spin transition, which becomes cooperative, I'll explain that in a minute, in connected systems. So we go from molecular materials like these to connected systems like these, to coordination polymers or coordination nets or chains, materials such as these. And experimentally, this is from an experimental paper, it is seen that these coordination polymers basically show hysteresis in their magnetic properties with temperature. And this hysteresis is also manifested as a bistability at a certain temperature, as you can see from the experimental figure here, where they show that at the same temperature you can have 2 states at 2 different colors. The colors indicate the spin state changes as well, which is also a very interesting thing, which I'll come to later. And the cooperativity is basically manifested as a hysteresis effect. So what is cooperativity? So cooperativity is phenomena by which you have, instead of this kind of a situation where you have a very gradual, almost a second order change and no cooperativity in a liquid or a solution, to an almost first order change, and for a very strongly cooperative system, you also have hysteresis. So you see that how the transition happens between the low spin and the high spin states is what determines the cooperativity, and long range ordering is basically essential for cooperative transitions. So strong cooperativity is mostly associated with first order phase transitions, and this cooperative behavior is manifested as the hysteresis, as you see here, and which was also shown experimentally. So, and the hysteresis effect obviously is associated with memory effects, and this is very important because we are always talking about memory devices and functional materials. So these can be used as memory devices because of the hysteresis effect. Now, what I am interested in is basically the mechanism of spin crossovers and spin transitions. So at the molecular level, this is very easy to understand. So when you have a large crystal field splitting, I take the example of iron 2+, which is in a D6 state. And when you have a very large crystal field splitting you have all the spins paired up and you have an S equal to 0 state in the T2G because it's an octahedral coordination, and your d orbitals are split between T2Gs and EGs. However, when you have a small splitting between T2Gs and EGs, the Hund's coupling wins this competition, and hence you have a spin S equal to 2 state. So this can be driven by temperature and pressure because the crystal field splitting depends on your iron or any transition metal to your P nitrogen P or oxygen P bond length and how much they overlap, and hence you can drive this easily by changing the bond length and the volume, and this can be driven by temperature or pressure. However, what is very interesting is what happens at the intermolecular level. So when you go to connected systems, when you go to coordination polymers or higher connectivity systems where long-range ordering is possible, so what are the two possible interactions? Well, mostly it has been identified that the two possible interactions could be magnetic exchange interaction J between the nearest neighbor super exchange between Fe2 plus centers, and the phononic excitations EV due to the elastic couplings between the Fe2 centers. So which among them plays a major driving role in driving the cooperativity in the system? That is what we want to figure out. So with that, we construct a model Hamiltonian which has somewhat been studied in literature, and this model Hamiltonian consists of various terms. So the first term is basically the intra-chain elastic interaction which couples the pseudo spins. Then you have a difference between in energy between the high spin and the low spin states. Then you have the magnetic exchange which couples the real spin quantum numbers, and finally you have some steric and elastic effects, steric and also electrostatic effects between the chains, which are very weak, mind you. And hence, mostly the strong interactions are the elastic intrachain interaction and the magnetic intrachain interactions. And if you solve this Hamiltonian, then you find that the EV can be written as a quantity which is kBt into k, where k is 1 by 8 log natural of E plus minus square by E plus plus into E minus minus. Now from here, it is easy to understand that E plus, the effective intrachain elastic interaction would be ferrotype if E plus minus is greater than root of E plus plus into E minus minus, and it would be antiferrotype if it is E plus minus is less than root of E plus plus into E minus minus. Now, why are these E plus minus and E minus minus and E plus plus different? Well, the elastic interaction EV is basically spin dependent. And why are they spin dependent? Because the sizes of the high spin and the low spin coordination centers are different because the volumes change. So the high spin has a larger size than the low spin, and the high spin is the E plus plus, the high spin low spin is the E plus minus, and the low spin is the E minus minus. And as you see that if you take this one, this distance as is A naught, then you have an A naught plus delta for E plus plus and A naught minus delta for E plus minus. So with this model in mind, let us move to the Monte Carlo simulations that we did to determine in a parameter regime, not taking any first principles assumption yet, what are the basic interplay between the ferroelastic and the magnetic and the antiferroelastic and the magnetic situations. So in case of a ferroelastic interaction, we plot the high spin fraction versus the temperature on a lattice model, and we find that there is already a hysteresis, and the magnetic interaction only enhances the hysteresis width in this case. However, for the antiferroelastic intrachain interaction, we find that there is absolutely no hysteresis, but however, this is still almost first order kind of transition going towards first order. So this is a weakly cooperative system, and the cooperativity increases and hysteresis pops up when you plug in the magnetic exchange. So for the antiferroelastic intrachain interaction, we have to remember that the magnetic exchange is very important to have a hysteresis effect and the memory effect. So next we move on to real material calculations. And what are the challenges for these material specific calculations? Well, of course, strong electron correlation, because it's an open D shell, and then the complex geometry of the material. And we need to also capture the electronic and the structural changes under the external perturbation of pressure or temperature. And our proposed methodology is DFT plus U coupled with ab initio molecular dynamics within DFT plus U regimes. And the possible materials showing cooperativity, well, mostly experimentally coordination polymers have been studied. We are proposing hybrid perovskites, which is a very new and important class of materials experimentally and has recently shown a lot of interesting properties, as also a possible candidate for showing spin crossover and cooperativity. And this has not been studied experimentally yet. So first, let us look at coordination polymers. We take the example of iron triazole, and from first principles calculations, we calculate the elastic interactions, and we calculate the E++, E+-, and E-, from the by fitting the energy versus iron nitrogen bond length, and we find that this is an antiferroelastic interaction. And when we plug these back into our Monte Carlo model, and then we obviously need the magnetic exchange, and when we plug also the magnetic exchange back into the model, we find that we can very well capture or reproduce the experimental delta T, that is the width of the transition, and the TC, which is the point, the central point of the transition, very well. So our hypothesis that first of all, antiferroelastic interactions require magnetic exchange can be verified with this, because if we did not put in the J or the magnetic exchange, we would not get the hysteresis region. To further confirm without any modeling, we do ab initio molecular dynamics. These are mostly Born-Oppenheimer AIMD, and this is a combination of NVT and NVE. And we find that at 10 Kelvin, our low spin state is stable. At 80 Kelvin, we have a bistability, which is the center of this hysteresis region. And as shown experimentally in the very beginning, there is a bistability which confirms the hysteresis region. And at high spin, at a higher temperature, the high spin state is stable. So in effect, with AIMD, with these energy profiles, we can show that the system goes from a low spin stable state to a bistable state at a moderate temperature of 80 Kelvin to a high spin stable state at 200 Kelvin. And with that, we move on to the hybrid perovskites, which we are now proposing as a candidate material for spin crossover and spin transition studies. A lot of properties have been studied, which are like multiferroicity, order disorder phase transitions accompanied by some hysteresis below critical temperatures, and various other very interesting properties. And this is being studied very widely experimentally. So can these materials show spin transition accompanied by hysteresis, and can this cooperativity be tuned? Well, we take three different examples: dimethyl ammonium iron formate, hydroxyl ammonium iron formate, and dimethyl ammonium manganese formate. And with these, we study the systems. We show that for both dimethyl ammonium iron formate and hydroxyl ammonium iron formate, a pressure-induced spin crossover is possible, and their critical pressures are very different. And we also show that when we release the pressure, we get hysteresis of different widths in these two materials. And this is due to the fact that hydroxyl ammonium iron formate is very strongly cooperative and very strongly ferroelastic, whereas dimethyl ammonium formate is less cooperative and less strongly ferroelastic. And we can also show piezochromism by calculating the absorption cross-section in both these materials. And we find that they have very similar, they are expected to have very similar color changes. However, their hysteresis widths are different, because you can tune the hysteresis widths by changing the A site cation and the hydrogen bonding, whereas you can, I'll show in a minute, that you can change the color of the color change or the spin cross piezochromism associated with spin crossover by changing the metal transition metal ion. So for this, we also show a very similar mechanism of spin crossover in dimethyl ammonium manganese formate. Here the spin crossover is also from a different material different spin states. So instead of s equal to 0 to s equal to 2, we now have an s equal to half to s equal to 5 by 2. And this is also driven by a pressure, which is a moderate pressure of 4.5 gigapascals. And high spin state has a much wider band gap than the low spin state. And this is what generates the difference in change in color, or the difference in change in piezochromism in this material compared to the hydroxyl ammonium iron formate and the dimethyl ammonium iron formate. And we find that in this material as well, we can show a pressure-driven spin crossover and a spin transition with a hysteresis with a reasonably large hysteresis width of 2 gigapascals with a PC of 4.5 gigapascals. And when we do ab initio molecular dynamics calculations with both NPT and NVE combination, and we can calculate the temperatures at which these changes take place, we can show that we have a TC of 275 Kelvin, which is almost very close to room temperatures, and delta T of 50 Kelvin, which is a reasonably large width of hysteresis. So this material is also ferroelastic, and the ferroelasticity gives rise to the very large cooperativity, and magnetic interaction helps in that. With dimethyl ammonium manganese formate, now we see that with various small changes in pressure, you see a change in the absorption spectrum and a large jump when there is a change from 4.2 gigapascal to 5.2 gigapascal, since this is where the color change happens. The very observable color change happens in this material, and this is very different from the color change that was happening in dimethyl ammonium manganese iron formate and hydroxyl ammonium iron formate. So the color change here from the absorption cross section, we can assume it to be yellow to black. However, we cannot say this merely from an absorption cross section, so we cannot say this very definitively. And with that,
just a minute left.
Yeah. So with that, I would like to summarize. So in summary, we have a spin crossover. We can go from a spin crossover molecular systems to spin transition and cooperativity in connected systems with long-range ordering and hysteresis. We show this in two different classes of materials. In the metal organic coordination polymers, we can show from our model that ferroelastic interactions are cooperative, whereas antiferroelastic are non-cooperative, and magnetism is essential for antiferroelastic interactions. And we prove this in a well-studied experimental material of iron triazole, and we can reproduce the TC and delta T. However, we also propose hybrid perovskites as the new materials in which spin crossover and spin transitions may be studied, and we can show that both pressure and temperature driven spin transitions and piezochromism exist in case of hybrid perovskites, and we study this with DFT plus Monte Carlo and AIMD, and this is a very useful tool for studying phase transitions in these kinds of materials. In hybrid perovskites, we also have a very interesting phenomena happening where the A site cation determines the width of hysteresis or the cooperativity due to the hydrogen bonding, the differential nature of hydrogen bonding of the A site cations, and the transition metal determines the color change of piezochromism. And there are a wide range of device applications which are possible with these materials. I won't go into outlook since I do not have a lot of time, but a lot of studies can be done with hybrid perovskites, experimental studies particularly, since these kinds of course, piezochromism has been observed experimentally in hybrid perovskites, but not in these classes of materials, and spin crossover has not been studied at all. And these are the relevant publications which led to this talk. This is a very new publication with it's not published yet. It's a preprint. You can see it on arXiv, and we hope to get it published soon. And I would like to acknowledge all the funding that I get currently from Professor Claire Gray and Andrew Morris, and these are the various collaborators that I've worked with on these projects over the years, and there are various funding agencies. And thank you for your attention and listening.
So Lewis will be telling us about, Lewis is from the University of Bath, I should say first, and he'll be telling us about polaronic effects on charge carrier scattering and mobility in lead halide perovskites. Over to you.
Yeah, thank you very much. Yeah, good afternoon, everyone. Yeah, thanks to the organisers for letting me speak on this. Yeah, we're going to be talking about polarons, particularly large polarons, their sort of incorporation into the theory of lead halide perovskite charge transport, and sort of whether or not they make a difference, and if so, what difference do they make? So for those that aren't aware, lead halide perovskites are a very interesting material right now. In general, they take this ABX3 formula with these sort of octahedra here. These octahedra are made of tend to be made of halides, and you've got inside each octahedra you have either lead or tin, and you have what's typically an organic but sometimes inorganic acite cation as well. And so this range of options means that you can tune your halide perovskite quite a lot. And the reason everyone's interested in them is for their optoelectronic properties. So people will be making really good solar cells with them, with high efficiencies, but with really cheap solution processed devices. And one of the big questions sort of in the field right now is there are quite a few significant problems with them as sort of functional materials. But one of the big sort of questions is actually, why do they work so well in the first place? And also just how do they work generally? What are the charge transport properties? What are the sort of key bits of theory that should be used to try and describe how charge carriers move in them? And so one of the sort of sub-themes of this has been the idea of large polarons. So this sort of traces itself back to a letter back in 2015 by Zhu and Podzarov, where they sort of hypothesized that charge carriers might be protected from scattering events by their incorporation into large polarons, which I'll explain in the next slide. And they sort of use this theory to explain some of the sort of slightly strange transport properties of halide perovskites, including they've got a bit of a strange mobility temperature dependence, which I'll get to at the end of this presentation, but also things like their exciton dissociation energies and a few other things as well. And this sort of over time has become a bit of a sort of growing consensus that the charge carrier dynamics in polarons can sort of be rationalized as large polarons, and that by sort of using large polaron theory, you can sort of explain away a lot of these things. So the question we wanted to answer was sort of how important are polaronic effects in halide perovskites? And to do this, we're just going to focus on electrons in methylammonium lead iodide, which is a bit of a fruit fly. You'll see also later we sort of expand this to holes and other halide perovskites as well. So a polaron is formed from the interaction between a charge carrier and the sort of ionic lattice that surrounds it. So electron hole motion can couple to particularly LO phonon modes in ionic lattices. And then if you try to move that electron or hole around, you can think of it forming a quasi-particle that's called a polaron, which sort of consists of this electron plus the lattice distortion. And for clarity, there's two different types of polarons that tend to be talked about. There are small or self-trapped polarons. Those have sort of thermally activated hopping transports. They're localized and they sort of have this Arrhenius transport and a mobility that tends to go up as temperature goes up. But what we're going to talk about here is the large or itinerant polaron. That has much more band-like transport. So they behave a little bit more like free particles. In particular, they tend to have a mobility that goes down as temperature goes up. And that's what we see in halide perovskites. So that's what we're going to focus on. So the basis of our model is going to be the Feynman polaron. And it's a sort of deceptively simple idea where you have your electron here of a mass ME, and you construct this sort of fictional particle that represents this cloud of virtual phonons, which also has a mass. And they get coupled together with this quantum harmonic oscillator, which I've sort of just described as a spring here. And so the Hamiltonian for this interaction looks like a sort of free particle, but just with a larger mass. This M is much bigger, well, a little bit bigger than the electron mass. And it also has this extra term which describes the quantum harmonic oscillator. And likewise, you have, when you look at the eigenstates, again, you have this free carrier plane wave eigenstate here just with a larger momentum and a sort of center of mass body coordinate, plus this a more complicated 3D harmonic oscillator term. So that's the basis of what we're doing. Now this work was done by Frost in 2017, which we sort of picked up and used again as our sort of starting point. So you take the free energy that was derived by Osaka in 1959, you minimize it to find just the two parameters that you need to fully characterize your polarons. That's the mass and the oscillator frequency. So for electrons and MAPI, we see that at room temperature, you get about a 40% increase in mass over what you would get in your regular band electron. And we also find that the harmonic oscillator frequency is proportional to the temperature. We also worked out the occupation of the ground state of the 3D quantum harmonic oscillator. And we see that for all temperatures that we're interested in, the occupancy is basically 100%. So we're going to carry on assuming that our polarons are always going to be in the ground state. Okay, we want to work out Polaron transport properties. So then we need scattering rates. So Kadanoff did some great work back in the 60s with his Boltzmann equation for polarons. And we're going to use this basis here, the sort of framework that he used, which was that we can compare electrons and polarons directly by using identical perturbing Hamiltonians for the scattering rates, so interactions with phonons or impurities. But we use the different eigenfunctions for the sort of free band electron and the large polaron. Using that, we can sort of compare them directly and see what differences polaron theory makes. So we derived scattering rates for polar optical phonon scattering as Kadanoff did. But then we also derived scattering rates for acoustic phonons and ionized impurities, which have sort of been claimed to be important in Halide perovskites in various bits in the literature. And I'll show you the scattering rates in the next slide. But the broad idea is that the scattering rates are very similar for all mechanisms, apart from a larger mass and an extra term on all of the scattering mechanisms, the effect of which is to inhibit large momentum transfers. So it's basically when you have a scattering mechanism, it can scatter by an angle, and it inhibits large scattering angles. This was noticed by Kadanoff. These sort of highlighted bits here are basically saying the same thing, as well as these extra transitions, which he later ignores as well. But this appears sort of to support this sort of shielding hypothesis, right? That Zhu and Podzarov were on about. But then when we run the numbers, we actually get very similar scattering rates for electrons and polarons, which are the dashed and whole lines here, for all of our scattering mechanisms, apart from acoustic. And even acoustic, although it's you get very different scattering rates at low temperatures, when you go up to room temperature, the rates tend to converge again. So the question is, we derive these rates that look a bit different. Why don't they actually matter all that much? So we decided to look at then this angular distribution of the final states after scattering. So once you have a scattering event, particle has an initial wave vector, and a scattering process can do one or two of two things. It can either it can change the magnitude, so you can gain or lose energy, and then it can also redistribute the direction of that wave vector, so it can scatter it by an angle. You can imagine when we're going to work out the mobility, if you get large angle scattering, that can reduce the mobility significantly. So we came up with these plots here, which I should probably explain because it's a little bit complicated. It's a polar plot. Up here you have 0 angles, and it works out it shows the probability density of scattering to a particular angle from 0 to pi as a function of the initial energy, which is the radial coordinate here, for band electrons, which is the left-hand side, and electron polarons, which is the right-hand side, so that we can compare them directly. And so the darker a color is, the more likely a particle is able to scatter into it from an initial angle of 0. As you can see for maybe this example one, this one's very strongly forward scattering for both band electrons and electron polarons, because all of the probability density is sort of clustered around here. So this is what it looks like at 100 Kelvin. So you can see that for polar optical scattering, both absorption and emission, and also impurities, you have this, for band electrons and electron polarons, the final state distributions are still quite highly anisotropic. But the adding the electron polaron terms sort of exacerbates that anisotropy. But what you can see is you start looking at the sort of magnitudes of probability density. Already for band electrons, polar optical phonon scattering is highly forward scattering. It highly favors small scattering angles. So our sort of idea is that although you have this extra term that inhibits large momentum transfers, you're actually inhibiting very few scattering events in the first place. What is different, we remember that acoustic, was significantly changed. You can see there's a qualitative change here. So at 100 Kelvin, acoustic phonon scattering is basically elastic, and it's also anisotropic. But introducing the electron polaron terms changes that significantly to be strongly forward scattering. So that's what sort of affects the change in the rates. And then as you go to 300 Kelvin, so we increase the temperature, you can see that all these differences sort of fade away and they sort of change. They become less significant. Okay, so with that, we want to now start to calculate some charge carrying mobilities, because that's one of the observables that can get measured. So we're going to define the mobility as the ratio between the drift velocity and the electric field strength. And one of the curiosities in Halide Perovskites, especially with MAPI, is that you have a mobility that follows about t to the minus 1.5 across a range of different sort of experimental techniques that give different orders of magnitude, but the same temperature dependence. Whereas if you just took sort of standard textbook theory, you'd actually expect a t to the minus 0.5 temperature dependence, assuming Froelich scattering with polar optical phonons. And so polarons have sort of been suggested to be able to explain this. So we solved the Boltzmann transport equation, which is written here. Our new forms of the scattering rates are a little bit complicated, so solving the BTE analytically is sort of impractical. So what we do is we use the Ensemble Monte Carlo approach to solve the Boltzmann transport equation stochastically and to calculate essentially exact solutions to the BTE. So the Ensemble Monte Carlo, I won't go into too much, but you essentially just follow the assumptions of the Boltzmann transport equation. You have these periods of free flight under an applied field, and then you stochastically scatter your particles between states according to the rates that we described earlier. And this has applications beyond what we're doing, which is in the steady state bulk. You can eventually, we hope to do sort of device scale simulations and also look at transient effects as well. But this is just the bulk for now. So these are the mobilities that we calculated. So first of all, in the blue here, we have the standard bare electron band results here. You can see that the temperature tends towards t to the minus 0.5, as you'd expect. And then when we add in the polaron terms, so all we have is the new rates and the large effective mass. So you can see the effective mass has led to the mobility overall dropping by about a factor of 2 when it gets to room temperature. But then you also look at the temperature dependence, and you can see, looking at, comparing with the experimental data in the background, you can see that the temperature dependence is actually shallowed rather than steepened, which, if our aim is to try and compare with experiment, leads us to sort of, believe that Polaron transport can't be sort of the only reason, the only thing that is needed to agree with experiment. We did this for other Halide Perovskites and also holes as well as electrons, just to prove that the overall results of our calculations are fairly general. So to sort of conclude, to wrap things up, for MAPI electrons at room temperature, large polaron formation, you get a mass enhancement of about 40% at room temperature, and a small change in the scattering behavior. There is an inhibition of large momentum transfer scattering events, but because the dominant scattering mechanisms in Halide Perovskites are already strongly forward scattering, this has a limited effect. And then finally, polarons alone don't appear to explain the unusual mobility of halide perovskites. So that doesn't mean that they don't exist, that it's not the sort of appropriate theory to use, but it means that they have to form part of a more complete model that incorporates, we're looking at the literature, so that things have been suggested such as anharmonicity or multiple phonon modes or sort of dynamic disorder. So they should be considered within the sort of framework of that. And then obviously we've only considered the sort of steady state mobilities. The effects on recombination and or exciton dissociation, they sort of still remain to be investigated and remain sort of open fields for inquiry. And with that, I want to acknowledge Alison Walker at Bath for sort of being my supervisor, and Matthew Will, formerly of Bath, now very recently in Aachen in Germany, for sort of leading the project as well. I want to acknowledge our funders, and also, if you're interested, the paper was published in PRB a few months ago. And with that, I'll take any questions. Thank you very much.
Lewis, thank you very much for a very clear talk. There's one question in the Q&A, so I'll show that on the screen. So the question is from Hambo Yang at Imperial. Why do electron polarons favor forward scattering?
Okay, so in general, sort of depend. Well, generally, different mechanisms can prefer forward scattering. In sort of the case of LO phonon scattering, it's because of the Q dependence of the Froelich Hamiltonian. So the Froelich Hamiltonian, you get much stronger scattering with smaller with phonons with a small wavelength. And once you sort of you're then limited by the sort of geometry, and that means that you get this sort of strong forward scattering. Why do the electron polarons favor forward scattering even more than that? Is a tricky question that I've not really got a good sort of intuitive answer for. Read the paper and the math says so, and that's the easy answer. But yeah, I've not really got a good intuitive reason for that. There'll be something to do with it being heavier, but there's another the quantum harmonic oscillator terms. Those are the things that sort of really give you the qualitatively different behavior there.
Okay. There are another question. Maybe I'll ask one. So you showed that your polaron mechanism doesn't explain the full picture, and needs to be part of a more complete. So would you care to speculate on what else might be the next most important factor?
Yeah, I'm trying to keep on top of the literature. There are a sort of range of different mechanisms. My thoughts are probably won't be all of them, but it may be several of them. So I mentioned a few in the conclusion. So there's some work being done by some people using sort of EPW that are claiming that multiple phonon modes are responsible for the explanation there, or the temperature dependence. My sort of the one I find the most convincing is a paper about dynamic disorder, I think. I can't remember the authors, but yeah, it's there in the literature. There's another one that claims that Rashba splitting encourages acoustic phonon scattering, which has a steeper temperature dependence, and inhibits Froelich scattering, which means overall you might get more favorable temperature dependence. There's also most of these theories are being done assuming parabolic bands, and I've not seen much work being done, taking into account the non-parabolicity of these bands. So lots of different things. It's a very complex material, but yeah, I don't feel like it's been solved yet. Okay, great. Okay, so that brings us to the end of this session and to lunch. Let me just say a big thank you to all the speakers in this session, Jacob, Hrishit, and Lewis. Thanks very much for sticking to time, and thanks very much for presenting such clear talks.